Lab 4 Circuits by Sarah Dea. So the description of this lab and purpose of it was to use the principles of energy and current conservation to predict the behavior of circuits with resistors in series and parallel, use multimeters to measure the values of conventional current and potential differences in circuits, and examine ohmic resistors and capacitors. So our results preview for the circuit time constant, I got 5.974 seconds, and the system is the circuit and the surroundings are everything else. We are also assuming that the resistance of the wires are negligible, the resistance of the ammeter is negligible, and the resistance of the battery is negligible. It's not. Some principles that we used were the conservation of energy slash charge, which says that the total energy slash charge of the system remains constant. The loop rule, which says that for a loop, the sum of the electric potential is the node rule, which says that for any node in the circuit, the current flowing into the node is equal to the current flowing out of the node. Steady state of circuit says that the current at each part of the circuit is constant. Ohm's law, which is the equation for current based on the resistance and change in the electric potential, which is this. Resistors in series and parallel with the following equations to find the total resistance. So this is in series and this is in parallel, and the capacitance equation, which is this. So in experimental model 1, so I predicted that the current in ammeter 1 and the current in ammeter 2 would be equal, and the resistance would be 147 ohms. That's these two added together, and the current that would be read from the ammeter would be 0.02 amperes. And in our model, the ammeter did read the values correctly, and if the ammeter is connected backwards, it would be the current value would be negative. And when we replaced one of the ammeters, this one, with the voltmeter, voltmeter read that the charge is 3 volts, but the ammeter read that there was 0 current. And this is because it's an open circuit rather than a closed circuit. And I also recorded the electric potential from each of these points, which I got here. And I also found the current reading through calculation. So I added up the electric potential, the total electric potential divided by the total resistance, and I also got 0.02. And basically the ammeter allows current to travel through it while the voltmeter doesn't. And when the ammeter is connected in parallel with a 100 ohm resistor, the ammeter reads 0.06 amperes because in this situation, the current has the option of skipping the resistor, so there's less resistance. And this was the plot that I made. So I drew this part from the values that I found earlier. And these are the resistor calculations that I found, which is the change in electric potential divided by resistance, or yeah. So in the second experimental model, by connecting the battery, capacitor, and the 10 ohm light, the bulb lights up, begins to dim, and then turns off. And when I connect the capacitor and the 10 ohm light by itself to discharge the capacitor, the bulb lights up, begins to dim, and turns off again. So when the capacitor charges, it takes away current from the circuit. And these are the calculated times that I did for the 10 ohm bulb, which is how long it takes the capacitor to fully charge, and then how long it takes the capacitor to fully discharge. These are my times. So in this part, the goal is to find the circuit time constant, RC, which we did by using the conservation of energy equation for the circuit. The electric potential of the capacitor plus the electric potential of the resistor is equal to 0. And then we plugged in respective equations for the electric potentials of each to get this equation, and then we linearized it using natural log. So the slope is equal to -1 over RC, which we got negative 0.1674. So RC equals 5.97371 seconds. And the percent difference is 0.43%. So these are the results. So what if you were doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? A real ammeter has some component of resistance, so in real life, the total resistance of the circuit will be larger than we thought. Also, for the experiment where we put the ammeter to the resistor in parallel, due to the ammeter's resistance, some of the current will be more inclined to go to the resistor than the ammeter, although not a lot. So in the experiment, the ammeter will read more than 0.02 amperes, but less than 0.06 amperes. So what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? If we had a model circuit with just a battery and capacitor, the capacitor would charge instantly. However, in real life, batteries have resistance in them, so it would take some time for the capacitor to charge, albeit much less than with a resistor. The main source of error is human error. During calculations, I may have misused the timer or written down the wrong electric potential when calculating. Also, the computer only rounds to the tenth place for time and hundredth place for voltage, so it might have a slight rounding error. In conclusion, for this lab,